Okay. Good morning, everyone. Let's get started. So first of all, we are only leaving a few lectures. I think the last lecture will be the next Thursday, and we have released all the assignments. So all the assignments required now is homework 5. So I believe we need to start looking at that. So there's only one workload for homework 5, just to implement backpropagation algorithm we discussed. Of course, if you're interested, we have some bonus problem asking you to implement logistic regression, which we're going to discuss today. So, but it's totally up to you. It's optional. And another thing is that for the final project report, please be aware. Please do not ask for personal extension when the deadline is approaching, because we're unlikely to grant personal extension. The reason I have emphasized quite a few times, because we have to meet the deadline to submit all the grades, and the Office of Registrar never gives us extension. So yeah, so don't ask for personal extension for the project report. If you believe that's kind of like taking you some time, please start doing it right now. And regarding the final exam, we would like to use the online exam. Will be at the same time as scheduled. I mean, it should be like from 8 a.m. to 10 a.m. If we can take a look at the course webpage, we have shown the course the exam time, which is consistent with what was scheduled by the administration. But due to the weather issue and the convenience issue, we're going to still follow our previous methods that we're going to do that online. We'll open a Canvas exam at that time. And the good thing is that you don't need to spend too much time preparing for the exam, because there won't be mathematical calculations, there won't be math proofs. Actually, you don't need to write any math in your final exam. The final exam will be mainly about single choice, multiple choices, and some text description, writing understanding about, say, perception or empirical risk minimization, writing down your understanding. So it's relatively easy, but it does request you to understand what we have discussed throughout this semester. So we'll in the final lecture, I mean next Thursday, I'll walk through what we have discussed throughout the semester. I'll give you some sense, like how you spend like this time to well prepare your final exam. Okay, so any question regarding the remaining things for this class? Everyone feels calm? No, we cannot offer that, because the exam is so easy. I don't want to spread that. Right. Any other question? Yeah, basically, if you have some, if you walk through the slides and you're sure you understand what our lecture slides are talking, you won't have any problem in the final exam. Right? Yeah, but if you don't understand any basic concepts in what we discuss in the class, yeah, you might have some trouble, right? But anyway, that will be no more than beyond your basic understanding about what we have discussed, right? We won't ask you to prove generalization error bound, right, for some particular type of classifiers, right? We won't ask you to calculate VC dimension of something, right? No, it's just the Canvas. The Canvas will create a final exam on Canvas, but you won't be able to open until that time. That was scheduled. I believe it's from 8 a.m. to 10 a.m. If we do this exam physically, you have to came here. You have to come here at early morning, very cold. If there's snow, that will be even more trouble, right? Why not you just get up and sitting in front of your desktop or laptop and doing things like, most of the students finish that in 1 hour, although we have allocated 2 hours for the final exam. Yeah. Another question? Yeah, we'll keep reminding you our schedule of final exam. It will be online. It will be from what time point to what time point, and until I guess 1 night before the final exam, and also 5 minutes before the final exam. Right? We want to make sure that everyone won't miss the final exam. Like if you happen to miss that, there will be it won't be easy to schedule another makeup exam. So don't miss the final exam. Any other question? Okay, great. Then I guess the remaining task for everyone is just to finish up your homework 5, finish up your project reporting time, and spend some time to doing some review, and then we're done with this course. Okay, so today we're going to talk about one instance of Bayesian learning paradigm we discussed in the last lecture. I believe it's last Tuesday, right? Which is called logistic regression, right? So so what I'm saying so far include like linear models, right? Linear models including perception, support vector machines, linear regression, and so on, right? Then we'll talk about nonlinear models. Right? We got 2 types of nonlinear models. Again, one. Yeah, SVM. What? KNN, of course, is nonlinear classifier, but we didn't cover it, right? Just want to ask, like, what kind of 2 types of the nonlinear models we have discussed? Yeah, kernel perception. Oh yeah, of course. Right. Kernel perception SVM all use the so-called kernel trick or feature mapping to implement this nonlinear reality, right? But we have also discussed other types of models. Yes, exactly right. And we can build up a nonlinear models from scratch, right? It's not necessary to always based on linear models, right? So the very first model, linear decision trees are nonlinear models. Right? If you can remember, although it's very simple, but the theorem boundary can be quite complicated, right? And then artificial neural nets, right? These are another way to build a nonlinear classifier from scratch. Right? And we talk about how we train or how we learn those models, right? No matter if it is linear or nonlinear, right? So basically, we're gonna have we need to craft a loss function, which measures how well a model fits the training data, right? For example, square loss, right? For example, hinge loss, right? But doing that is called empirical risk minimization, right? Empirical barrier increment. Empirical means that, okay, because my training data is sampled from some unknown data distribution, so empirically it fits the training data, so we expect it will generalize well, right? But we also discussed, like, both from the computational learning perspective or from empirical perspective, we see that if you only minimize the training loss, we might have the risk of overfitting, right? If you happen to overfit noises or errors within data, then it will hurt your generalization badly, right? So that's why in practice, we're gonna always add some regularizer, right? For example, in SVM, we add a regularizer which is half of the square norm of the weight vector, right? And those regularizer, in essence, penalizes overcomplicated hypothesis space, right? We kind of like seek for hypothesis space which is as simple as possible, right? and plus the loss term, right? You want to find the best trade-off, right? Best balance between your data fitting and your model complexity, right? So this framework is called empirical risk minimization, right? So you will see that when we talk about logistic regression, the learning still falls in these two frameworks. Either you can do empirical risk minimization, which essentially corresponds to the maximum likelihood estimation, right? Or you can do regularized empirical risk minimization. You see that in the probabilistic world, it is called MAP estimation, maximum A posterior estimation, because you want to assign some prior over the model parameters. You will see that later. So here's our plan today. So first, we're going to define the model, the logistic regression model. Right? Then we'll talk about how we're going to train a logistic regression classifier. So it's a classification model. And then we're going to associate our training procedure to the learning framework we have discussed, right? We talk about empirical risk minimization, and regularized risk minimization. Right? We're going to make the connection to the two frameworks. Okay, first, logistic regression. Right? So if we could recall, for the Bayesian learning framework, we'll talk about two notions, right? One notion is that, okay, I'm going to learn a probabilistic concept, meaning that I'm not going to map my input feature vector to a binary label or discrete label, 0, 1, or maybe -1, 1 are more convenient, right? This is a SVM or other linear classifiers we have are doing, right? But in the Bayesian notion, right? In the Bayesian learning notion, we're going to do this, right? We actually map X to a probability. This probability characterizes what is the chance that the label of X is 1. That's why it's called regression, because the probability is a continuous value between 0 to 1. Right? It's not a discrete value, like either 1, -1. It could be 0.56, just meaning that, okay, you believe the chance the label of X is 1 is 0.56, right? If it's 0.9, you have a higher confidence to classify X to be positive, right? If it's 0.1, you might probably classify X to be negative, right? So that's the setting of the logistic regression, right? We want to learn a probabilistic concept rather than just a discrete classifier, right? So, but our data is the same. Like we still assume we have an input feature vector, d-dimensional input feature vector. Our training data are binary labels, either -1 or 1. Right? Suppose we have a training data set S, which contains m pairs of the feature vectors and binary labels. So, although our output data is discrete, right? Either -1 or 1, but we want to use this data to learn to predict the probability that given X, the label is 1. Right? So it's a continuous label. Right? So again, that's why although we're working on a classification task, logistic regression essentially is doing a regression, because you're going to regress a continuous value, although this value must be between 0 and 1, because it has an interpretability, right? It interprets the prediction as a probability, right? And then, given this formulation, we can have many hypothesis spaces, right? And here, for the logistic regression, we're going to use a very simple hypothesis space. So we model this probability, given X, right? We model the probability that the label of X is 1 as a sigmoid function. sigmoid function composite by a linear combination of x, right? So you can see that W transpose X here is a linear classifier or linear regression, right? We kind of like doing a linear combination of the input features with some weights, right? And then we do a sigmoid transformation to transform this score into a probability because the sigmoid is always between 0 and 1, right? And that's it. That's our logistic regression model. Okay. And here, again, for simplicity, we assume X has been augmented with a constant feature 1. So your weight vector contains not only the feature weights, but also the bias parameter B, right? So if you want to write it, if you want to expand it, it should be W1, X1 plus plus W, say WD, XD, and plus B, right? And it is essentially represent this, right? So, and then once we calculate this linear combination, then we squash this score into sigmoid function by sigmoid function, and then we get the probability value between 0 and 1. Okay. So any questions so far? Is everyone comfortable? Yeah. We can see that's just a straightforward extension of linear regression, right? And the only difference is that, okay, I apply a sigmoid transformation to transform this score. This is also a continuous score, right? Into a right range between 0 and 1. And that's it. And then our hypothesis space for logistic regression will consist of all functions of this form, right? So you can see that each hypothesis in our logistic regression model space has the same form, and it varies along with the choice of the model parameters W, right? So different W will correspond to different hypothesis. Right? And the nice property of the sigmoid function is that the input of Z can be unbounded, right? Z could belong to -infinity to infinity, right? And the output domain, sigmoid Z, is always between 0 and 1, right? That's why we choose sigmoid function. But in practice, sigmoid function is not the only choice. There are other transformations as well. For example, the standard Gaussian CDF, cumulative density function of Gaussian distribution, right? So usually divided by phi. So you can view it as a integral from -infinity to Z, and this is Gaussian density, and over dz, right? So if you use this instead, this is called probability regression. And it's very popular in Bayesian Bayesian learning of this classifiers, right? But in practice, sigmoid function is more widely used. Okay, any questions so far before we proceed? Great. Right. Here is the curve of a sigmoid function, right, to give us a more concrete sense how sigmoid function behaves with varying input, right? So you can see that actually when Z equals to 0, if you substitute 0 for Z into sigmoid function, you'll get the probability. The output of the sigmoid is 0.5, right? And when Z get bigger and bigger, right, sigmoid function will get closer and closer to 1. Right? And on the other hand, if you Z gets smaller and smaller and to be very, very large negative, not large, absolute value of the Z becomes large as well, but it is negative value, then the sigmoid function will quickly will quickly approach 0. Okay. So that means if your skew of your score z is very large, then your sigmoid function is very, very close to 1 or minus 1, 1 or 0. Okay, so there's also another nice property of sigmoid function, which we have covered before, right? That is, how do we calculate the derivative of sigmoid function? Right? So just do a quick review again. Right? If you take the derivative of sigmoid function with respect to its input z, right? Just apply the chain rule. You take the square of the denominator and then take the derivative over this exponential term, right? When you view this as a whole, you take the derivative for something like z 1 over z, you got a minus sign in front of it, and then you take derivative over this guy, you got minus sign in front of it. So the two minus sign will cancel out, right? So that's why we end up with this, right? You end up with e to the power minus z over square of the denominator, right? And a very nice observation will be, okay, if we expand this square, right? We write it as e to the minus z over 1 plus e to the minus z times 1 over 1 plus e to the minus z, right? You'll find that this guy actually is 1 minus the sigmoid function, and this guy is the sigmoid function. That's why we can conclude that the derivative of sigmoid is actually the sigmoid times 1 minus sigmoid. Right? That's a very, very useful trick when you implement logistic regression classifier, or if you choose your neural network to use sigmoid activation. And also because sigmoid function is always non-negative and less than 1, so sigmoid times 1 minus sigmoid will be non-negative, right? So what does it mean? Yeah. So now it matches the shape we have seen, right? It's a monotonically increasing function. Why? Because the derivative is always non-negative. Okay. So now we're going to model, given the label y, right? What is the likelihood that of your, what is the likelihood, right? So when y is 1, then the likelihood of your positive label is just this probability, right? Which is just sigmoid of your W transpose X, right? However, when you observe y equals to minus 1, because we model the probability that y is 1 is sigmoid of W transpose X, right? Then the likelihood of y is minus 1 will be 1 minus this probability, right? Does it make sense? Right? Remember, likelihood just model the probability you see this data point, right? You see the data, when you see the positive label according to a model, your probability is just the sigmoid of W transpose X, right? And when you see a negative value, of course, it will be 1 minus your sigmoid W transpose X. And then you can see that if you subtract 1 by your sigmoid function, it will become this, right? Okay. It's 1 minus this guy, and if you just do some simple calculation, right? You know you're going to replace the numerator by this exponential term. So if you do some dividing, right? If you divide both the denominator and the numerator by this exponential term, you will see that the likelihood for a negative label will be 1 plus 1 plus 1 over 1 plus e to the power of W transpose X, right? Compared to the likelihood for the positive label, what's the difference? What's the difference? What's the difference between these two likelihoods? Yeah, there's only one additional minus sign here, right? Does it make sense? Right? So you see that the likelihood for positive y, right? The likelihood of y being 1 is this guy, right? And the likelihood of y being -1 is this guy, right? The only difference is, okay, in the first case, you have an additional minus sign in front of W transpose X, right? Then what does it mean? It means that we can unify these two likelihoods together, right? How can we unify it? How can I use one formula to represent the likelihood for both cases? Negative y or -1? Oh, yeah, you're right. Yeah. Okay. So the idea is that I'm gonna multiply this score by y. Then you can see that this form covers both cases. One case is y is 1, one case is y is -1, right? So we can check, right? When y is 1, it just minus W transpose X, right? So it's the same as this guy, right? When y is -1, in that you'll see a negative label, right? Y is -1, minus, it cancel out. So it becomes W transpose X, right? In the exponent of the EXP. So you'll recover this form. Right? So you can see that actually we can use one expression or one likelihood form to summarize two cases. Right? Any questions so far? Is everyone feeling comfortable? Yeah. Classification problem, because our label is either -1 or 1. The reason is that we're gonna predict a probability. The probability you classify X to be 1. Right? And then you can accord to your probability to decide you're gonna assign label 1 or -1. Does it make sense?
Yeah, so
No.
it's a regression problem for the.
Yes. Because there's some benefit of doing this, because I can give you confidence. And then you can, according to this confidence, it's up to you how you're gonna decide to classify the label as 1 or -1. Semicolon, the thing is after semicolon just means the model parameters, because you want to learn these model parameters. But y and x are given, right? In the training, your y and x are the training input and training output, right? And in testing, your x is given, right? But you're gonna predict what's the probability of y equals to 1. Right? All these are decided by the step you want to learn W from data. Any other question? I mean, I'm happy for any kind of interaction. Yeah. But if you feel this is really straightforward, we can just proceed. Y equals to what?
But you said we're trying to learn against the right? So what if we thought that we such that
Yeah. Yeah. The notation here is just means your label takes Y. Y, of course, it has two choices, either 1 or -1, right? It just tells you, okay, if you take your label, meaning Y is 1, then it returns this, right? If you take a label to be -1, it returns this. Another question? Okay, great. So now we have our model, right? We have modeled what is the likelihood that given your feature vector, given your model parameters W, what is the probability that your Y equals 1 or your label is 1, right? And suppose we have learned a model, right? Meaning that we know what is the good W, right? All from data, right? How do we apply our logistic regression? So as we just discussed, right? Given any testing input X, right? I can use my model to calculate what is the chance, what is the probability that Y has label 1. Then according to this probability, we can decide whether we're gonna assign X as positive label or negative label, right? If you don't have any prior knowledge of prior references, you probably will just take 0.5 as the threshold, right? If your probability of Y being 1 is bigger than 0.5, you might want to classify X to be positive. Otherwise, you're going to classify it as negative. But this is not always the case. For example, you have a strong belief that, okay, this probability must be bigger than 0.8. I mean, you're super confident this label should be 1. Then you classify as 1. If it is less than that threshold, you're going to still classify as negative. It is possible you choose such kind of choices. It really depends on the application. If we're going, for example, in some cases, I would like to say, okay, correctly predicting a positive label is very, very important, right? So I need to make sure that if I classify this example as positive, it has a little chance to make a mistake, right? In that case, I might increase my threshold, right? For example, if I want to do a diagnosis, right? I want to diagnose some patient. Maybe this patient has some bad disease, right? So if I tell you this patient has this disease, right, you must make sure this diagnosis is highly unlikely to be wrong. Otherwise, they accept your diagnosis result and start treatment, right? And then eventually found that they actually don't have that disease. You got a lot of bad consequences, right? On the other hand, like even you increase the threshold, you probably the patient has that disease, but you say, but because threshold is too high, you're gonna still predict it's negative, right? It's not, but you can see that, okay, according to my test, I don't have sufficient proof to show that you have that disease. You can try another diagnosis test, right? That will have much lower risk than you falsely classify someone has some disease and put some treatment on them, right? So that's why in practice, you have such kind of a score, and to give you some basis to make decision is very important, rather than directly tell this guy has this disease or not have this disease. So okay, so now we have introduced the logistic regression model, right? Next, we're going to talk about how do we train a logistic regression classifier from data, right? So we're going to first talk about how do we perform maximum likelihood estimation, right? Which corresponds to the so-called empirical risk minimization, right? And then we'll talk about we want to add some prior over the model parameters. Then our learning becomes a maximum a posterior estimation or MAP estimation, which corresponds to the so-called regularized risk minimization principle. Okay. Again, let's go back to the problem learning. Suppose we have collected M training examples, which are pairs of input feature vectors and the label. Right? Label is either -1 or 1, right? And what we found what we want is that we want to find a model parameter, which is weight vector W, such that this probability, the probability of data, namely the likelihood of data, is maximized. Okay. And here we know that our examples are drawn independently and identically distributed, namely IID assumption, right? Then the question is, how do we proceed? Our idea will be just write down the likelihood of data, right? Because those data points are IID, so their likelihood can be written as the product of the individual likelihood of each data point, right? Which is just product from I to M, right? We have M training examples, and for each training example, we have a likelihood P of yi given xi and w. Okay. Then we want to maximize this data likelihood with respect to model parameters w. Okay. That's why it's called maximum likelihood estimation. Does it make sense? Okay. But the problem is that, okay, because each likelihood is just the probability, right? It's between 0 and 1. If you multiply a lot of probabilities altogether, it's easily to get on the floor, right? Meaning that your probability could be 10 to minus 29, right? That's too small, right? It could on the floor. So to be numerically stable, a common used trick is to convert the products to sums by taking the log. Right? We can take a logarithm over that. Why can we take a logarithm? Because logarithm is a monotonic increasing function. If you take a logarithm and do the maximization or minimization, it doesn't change the optimal value at all. So that means we do the maximization over the likelihood of the whole data is equivalent to maximize over the log likelihood, right? If you take the log likelihood over this product, now our objective becomes a summation of the log likelihood of each label given xi and given current model parameters w. Okay. Any question? Okay. Then we'll just look at the form of the likelihood, right? We just, as we previously mentioned, right? The likelihood can be written as a sigmoid function of the label yi times the score, right? W transpose xi, which has this form. Then you take a logarithm over that. Okay. What's that? Remove the minus sign because this is a power of -1, right? And put minus sign outside of its logarithm, 1 plus e xp minus yi w transpose xi, right? So it is equivalent to solving this, right? Equivalent to maximize the summation of negative logarithm of 1 plus e to the power of minus yi w transpose xi, right? And then if we can just get rid of this minus sign, then we're gonna change max to min, right? Maximize the negative stuff is equivalent to minimize that stuff, right? So it is equivalent to minimizing summation of the log 1 plus exp to minus this guy, right? Then what's the remaining thing? How do we minimize this summation? What? Yeah, you take the first derivative, you take the gradient, right? You can shove it into stochastic gradient optimization or any other gradient-based optimization. They optimize W. That's it. Okay. So now, let us look at the whole procedure, right? Our goal is to maximize the likelihood of the training data, right? So to make it convenient and numerical stable, we'll take a logarithm of the likelihood and get rid of the minus sign. Finally, we convert this maximal likelihood estimation into a minimization over a summation of some function over every training example, right? This function logarithm of 1 plus e to the power of minus yi double transpose xi is called a logistic loss function. It's a loss function. And imagine for the SVM, we have a different loss function, right? Which is called hinge loss, right? So to contrast, okay, hinge loss, something like this, right? Y minus y transpose w, right? So you can see it's very similar, right? So the hinge loss also share this term, right? Y w transpose xi, y w transpose xi, and logistic loss also use this term. But how do you, according to this term, and get your loss value is a different story. Okay? So that's why we call it logistic loss. Okay, so this is how we conduct maximum likelihood estimation. Any questions so far? Okay, so now let us move one step forward, right? We could also add a prior over the weights, right? Rather than just do not assume any prior assumption over weights, right? Suppose we want to add a prior over the weights, how should we do that, right? Now here we're going to choose a very commonly used prior distribution, which is called a normal distribution. We assign a normal prior distribution with zero mean and some standard deviation sigma over the weights. Right? So that means our prior over the weight parameter here, weight vector, is written as a product of the Gaussian normal distribution, where h mean is 0 and the variance is some unknown standard deviation sigma. Right? This is just the Gaussian density. Now, if we want to combine the prior and the likelihood together to get estimation of model parameters, we use the so-called map estimation, right? Maximum A posterior estimation, right? So why this is called maximum A posterior estimation, right? Because we add this additional prior, right? And then we're gonna combine this prior distribution with our likelihood, which is here, right? So remember, in the maximum likelihood estimation, only maximize the likelihood. But here we're going to maximize the prior multiplier with the likelihood. And because the posterior is proportional to prior multiplier with the likelihood, so you maximize the product between prior likelihood is equivalent to finding the weights who has the largest posterior probability. That's what we have discussed previously, right? So let's see the concrete step, right? We want to maximize the posterior probability of the model given the data, right? In other words, to find the most probable model given the data, which is represented by the P of W given S, right? S our data, right? W our model parameters, right? Which this posterior probability is proportional to the prior of the W times given W, what is the likelihood of the data S. Okay. So now I want to find out the most probable model, means that we want to maximize this posterior probability, and which is equivalent to maximizing the product between the prior and the likelihood. Right? So now let's just shove the prior and the likelihood term into this product, right? First, again, we're going to take a logarithm to simplify the term, right? We take a logarithm over this product. Now the problem becomes maximizing logarithm of the likelihood plus logarithm of the prior, right? And the logarithm of the likelihood, as we have derived, is just the summation of the negative logistic loss over every training example, right? And the logarithm of the prior, which we use Gaussian prior, right? If you take a logarithm of this prior, right, you will see that it becomes a summation of the square of each weight elements over the variance sigma square, right, plus some constant, right? Because this guy is just constant; they have nothing to do with W, right? We can just ignore it during our optimization, right? And then we can see that the maximum A posterior estimate is essentially doing maximization of the negative logistic loss over all the training examples plus summation over negative square of each weight over some sigma square, right? It doesn't matter. It doesn't matter. We can use whatever base, right? Because any log function is a monotonic increase, right? It doesn't affect the optimum value of W. And again, we can, I mean, because this minus sign is really annoying, right? We can just get rid of it and then change max becomes mean, right? Then it becomes our final objective, right? Which is essentially minimizing a summation of the logistic loss over every training example plus this guy, right? It's just a square norm of a model parameter vector W or some constant sigma square, right? Okay. Compared with the maximal likelihood estimation, we have an additional term, right? This actually corresponds to the regularization term, right? Remember, in our SVM objective, right? It will be half W transpose W plus the summation, right? You got hinge loss. Right? This is your SVM objective, right? So when we doing the map estimation for the logistic regression, after several steps of simplification, we return to a very similar form, right? The only difference is that, okay, I'm gonna replace the hinge loss by the logistic loss, right? And I got some, sorry, we got a constant C here, right? And the sigma square actually is counterpart of constant C, right? You can multiply sigma square here and put sigma square in front of that, right? Then it takes the same role as the trade-off parameter C in the SVM, right? So you find a very high similarity to the SVM loss. So actually, you can see that learning a logistic regression in a map estimation framework is also an instance of the so-called regularized empirical risk minimization, right? We have regularizer, which is exactly the same as the SVM, right? The only difference is that for the loss term, we switch to the logistic loss. Right? And in our homework, you got some bonus point. If you want to do that, you can try to use stochastic gradient descent to minimize this objective function, right? You should be able to write down the stochastic gradient descent algorithm for this training. And historically, we can also choose other training algorithms. Like we're not necessarily stick to stochastic gradient descent. You can use LBFGS or any other gradient-based approach because calculating this full gradient is relatively easy. Any questions so far?
Like seeing that we have like some prior then why don't we just say like, oh, we did this meeting with that, right? Why do we go through that? And we're like,
you mean you want to take W to be the mean of the prior distribution?
Yeah.
But what's the mean?
I mean, don't we know what the prior distribution?
Yeah, you know the prior distribution. Here we choose the prior distribution to be zero, mean with zero, and some noise variance, not noise variance, some variance sigma square, right? If you take the prior mean, then just W is zero. That won't give you a good predictability, right? You have to learn appropriate value of W from data. Right? Data is very, very important to tell you what is appropriate W, right? Usually you cannot assume W is zero. But I mean, here we use Gaussian prior, right? But in practice, another very common use of prior is called Laplace prior. Why? Because people believe that among this 1 million feature, which could be thrown into this logistic regression, many of them are useless. Right? So they want to drive a lot of weight elements to be 0. In that case, the Gaussian prior won't be very good. Instead, you're gonna assume, you're gonna encourage your weight to either center around 0 or far away from 0. Right? So in that case, you're gonna assign a much stronger prior, like Laplace prior. And then during the learning procedure, you can drive your learning of W. Many of these elements are encouraged to be 0 directly. Okay. But here we just use a very simple and common used choice. Another question? Okay. Yeah, so in case that you want to implement your SGD for map estimation of logistic regression, so I will just write down the algorithm framework, right? But deriving the gradient should be our job. Should be our job. Okay. So it's like very similar to the SGD framework we have done before, right? So suppose we got your training example, your M training example. So x1, y1, m, ym, okay. And remember each yj is either -1 or 1, right? J is less than or equal to 1, bigger than or equal to 1, less than or equal to m, right? So now our first step, okay, our SGD framework, our first step is to initialize the weight vector, right? For example, a commonly used initialization is just initialize it to be 0, right? And then we're gonna go through many epochs, right? Suppose I'm gonna work on this for big T epochs. Of course, the choice of big T is some hyperparameter. You need to choose that either from cross-validation or from other methods, right? And then inside each epoch, you're gonna first randomly shuffle the data set S, right? Then you're gonna go through every example, right? For every x, j, yj in the stream, right? You shuffle them, then you stream your data set S according to that random order, right? And then what you need to do is that you need to calculate stochastic gradient, right? The stochastic gradient is based on the so-called stochastic objective, which is you need to duplicate this example for m times, right? Remember, we have regularizers. That's why you have to duplicate this example such that you fake a data set to be of the same size of the original data set, right? You want to match the skew between the regularizer and their true data loss. This is what we have discussed previously. You have to make sure that this is to make sure that your stochastic gradient is unbiased. Okay. So that means you're gonna multiply your loss, right? Logistic loss, 1 plus exp minus yi xj transpose w, right? Plus your regularizer, right? Then you take the gradient, right? You use this gradient times some step size and to perform the stochastic gradient descent, right? Does it make sense? Right? This is also how we do the stochastic gradient descent for SVM, right? The only difference is that for SVM, we're gonna replace this logistic loss by hinge loss, right? And then we finish one update, right? And then we move to the next example. We calculate the stochastic objective, then do the gradient, calculate the gradient, and perform the stochastic gradient descent, right? We keep doing this until we finish processing the whole data set for this epoch. Then we move to the second epoch, right? Until we finish all the epochs, and then eventually we're gonna return our model parameters W, right? Any question? Okay. Okay. So the last part we want to talk about is the connection of our maximal likelihood estimation and map estimation for logistic regression to our previous learning framework. Okay? So actually we haven't pointed out this connection, but we'll now want to list those loss functions we haven't seen so far. Right? Okay. So in the loss minimization framework, right? Also the framework we have discussed so far about training a variety of models can be summarized as follows. The setup is we're assuming every example X is drawn from some fixed yet unknown data distribution D, right? And those examples are drawn independently. Okay? And there should be some hidden Oracle classifier F, which gives the ground truth label for every example X, right? Then our goal is that given the hypothesis space, we want to find a hypothesis H that mimics F, right? Or approximates F. Right? This ideal situation is that we can have some loss function directly penalizing bad hypothesis. Okay? Then we denote this loss function L, right? And then for every possible example X, input example X, right? We're gonna compare your hypothesis prediction and your ground truth labeled by F, right? We have some penalty or we have some loss function value, right? We want to minimize the expected loss over the example X on the data distribution D, right? We want to minimize this, right? This is our ideal training objective. But in practice, because data distribution D is typically unknown, it's highly complicated, right? So in practice, we're gonna approximate this expectation by some empirical estimate. How can we do that? We just sample a bunch of X from D, right? That is your training inputs. Then you take the average of the loss over every sample of X, right? This is called a empirical loss. Right? Why is it called empirical loss? Because your whole loss is an empirical estimate of this expectation. Right? And then learning amounts to minimizing empirical loss on the training set. Right? And is there a problem here? Yes, it is, because it brings the risk of overfitting. So we need something that biases the learner towards simple hypotheses, right? Meaning that I want to penalize the model complexity simultaneously, right? We do not want to always pick up the model who is so expressive, so big enough so that it can well fit, 100% fit every training example, right? So that means in practice, we always choose a regularizer which penalizes complex hypotheses, right? That's how we get the empirical risk minimization, right? The regularized empirical risk minimization. So this is called empirical risk minimization. Now we add a regularizer over the hypothesis H. We got this so-called regularized empirical risk minimization objective, right? And one Raynaud instance is SVM, right? And the regularizer is simply half of the square norm of the weight vector, right? And loss, they choose the so-called hinge loss, right? But in general, we are free to choose a wide variety of regularizers, a wide variety of loss functions, right? And our only requirement for loss function is that this loss should penalize mistake. Right? If you make mistakes in predicting the true label, you should give some penalization. You don't want your learning to keep making mistakes. Right? So the ideal loss function for a classification would be just a binary loss. Namely, it will only penalize wrong prediction. Like if your prediction is wrong, now I'll give you loss value 1. Right? If your prediction is correct, I don't have any loss. Right? I have a 0 penalty. Right? However, in practice, if you just minimize the 0, 1 loss, is very difficult. Why? Because this is a step function. Right? It's just a step function. It's either 1 or 0. Right? If you want to calculate the gradient from 1 back to your model parameters, it's very hard. Right? That's why in practice, I mean, although in theory it has many like theoretical properties, it's nice, right? But in practice, people will never use that because it will make your learning of the model parameters a big headache. Right? So in practice, we always need some surrogate. We come up like some much easier to deal with and smoother surrogate for the 0, 1 loss. Right? And all the loss functions we have seen before can be viewed as some kind of surrogate of the 0, 1 loss. So now we can list them, right? We have a perception loss, right? If you could recall, the perception, although it's mistake-driven algorithm, it can be viewed as minimizing some particular loss function, which is maximum between 0 and minus y W transpose x, right? And the hinge loss, the only difference is that you put positive 1 in the right iterm of maximization, right? And for eta boost, actually there's some theory and linking to the loss as well. It has some exponential form of loss, right? And the logis loss, what we have discussed today, right? Is logarithm of 1 plus is e to the power minus y W transpose x, right? So if we put all those loss functions together, right, we can have a zoo of loss, right? A different loss corresponds to different machine learning model, right? So you can come out you can add one new member in this loss zoo, and mark your name, right? So we can just take a look at the different loss curves, right? First one, this one, like this. This brown one is a 0, 1 loss. You can see that's a step function, right? If you make a correct prediction, so this one is just the y W transpose x, right? If it is positive, that means that you make correct prediction, right? If it's negative, that means you make a wrong prediction. So you make correct prediction, then it is loss is 0, right? If you make wrong prediction, it becomes 1, right? And then this one is hinge loss SVM, right? You can see that the interesting property of the hinge loss is that your score, your y W transpose x, must be bigger than some value. Here is 1. You are completely without any loss, without any penalty. That means your loss is 0. Otherwise, in some region, even you make correct prediction, you still suffer from some kind of penalty because you're making your data point to be too close to the margin, right? And of course, if you make a wrong prediction, you're gonna have some loss, right? And if you take a look at perception loss, you see that is actually just to move the hinge loss toward the left. Right? It sounds reasonable, right? Because it's at least at half part is the same as the 0, 1 loss. It only make the penalty when you make wrong prediction, right? And if you make a correct prediction, it doesn't have any penalty. Okay? And similarly, you can see the exponential loss. Right? Exponential loss that is used in eta boost is actually an upper bound of the hinge loss used in SVM. Right? And the last one is our logis loss. Right? It seems like not belong to any of them. Right? It's just in between. Right? But again, this is far from enough. I mean, far from comprehensive, right? You can come out whatever loss function you like to show when you would favor penalty, when you should decrease the penalty, and so on. Okay. So now we have finished up our discussion of logistic regression. But before we do the summary, any questions so far? Everyone feels comfortable? Okay. So we have discussed the logistic regression to give an introduction today, right? So to summarize, logistic regression is a classifier, but the classifier is a little bit different from the classifier we discussed previously. This classifier predicts the probability that label is 1. Okay? So that's why this prediction is of value, is a continuous value, right? And then you can use this probability to make a decision. What's your final label prediction, right? And we have 2 training methods, right? We can either use maximum likelihood estimation or maximum A posterior estimation, okay? And there's an interesting connection between the loss minimization framework we have previously discussed, right? Maximum likelihood estimation essentially corresponds to the empirical risk minimization, right? And the maximum A posterior estimation corresponds to the regularized empirical risk minimization, right? And the logistic regression is associated with so-called logistic loss over the training set. Okay, so after this class, we expect that you will be able to implement your own logistic regression classifier. Of course, it's not required in a course assignment, but you should be able to, or you should be confident that I can implement by myself. Okay? And this is actually very, very popular in industry. Like, although logistic regression seems very simple, but in industry, like a baseline model, for example, a baseline model for online advertising, or in Amazon, like product recommendation, is just logistic regression. They're going to collect user features, item features, time, and also user and also web page displacement and cookie profiles, all kinds of. They can extract millions of features, or even billions of features, and throw them into a big logistic regression model. If you are interested, you can take a look at a machine learning platform. It's called Wabi, VW, which is implemented by Microsoft Research. It was originally designed for logistic regression. There was a streaming and distributed learning framework of training logistic regression models super fast, and can do like 1 billion training examples and 1 billion or even 10 billion features together. I did that. I did use that when I was an intern in Yahoo Research 7 or 8 years ago. It's very, very impressive, right? And it's also it's open source. Everyone can use that. And we found that interesting. It works really well. It works better than many other machine learning models who seems much more complex, much more advanced. Yeah, but anyway, just to share, I want to just share some interesting story, interesting experience I have for the logistic regression. Okay, I guess we can stop early today, and see you on Thursday. Oh, by the way, the office hour today is changed to from 11:30 to 12:30, because we have some schedule on 1 p.m. So if you have a question, please stop by earlier.